I did Hippocrates' Quadrature of the Lune. Um, basically, a lune is a plane figure bounded by two circular arcs, that is a crescent. Hippocrates not square all such figures, but just a particular lune. His argument rested upon three preliminary results: the Pythagorean theorem and angles inscribed in a semicircle is right. The areas of two circles or semicircles are to each other as squares on their diameters. And we have area of semicircle 1 and over area semicircle 2. The first two results were known long before Hippocrates came along. The last proposition is more sophisticated. It gives the comparison of the two areas of two circles or semicircles based on the relative areas of the squares structured on their diameters. One of the semicircles has 5 times the diameter of another. The former has 25 times the area of the latter. There's a widespread doubt that Hippocrates actually had a valid proof, and he thought that he could prove it. Many scholars felt that this theorem presented logical difficulties far beyond what he could have been able to handle. His plan of attack was to first establish that the lune in question had precisely the same area as the shaded triangle. He could then apply the known fact that the triangle can be squared to conclude that the lune can be squared as well. And here's a theorem and the proof. Here's just Hippocrates of Chios. He wrote, "Squared the lune that made many other discoveries in geometry, being the man of a genius when it came to constructions, if there ever was one." In conclusion, with all he accomplished, the Greeks were optimistic about squaring the circle. Ancients devoted much time to this problem, and some later rites attributed on an attempt. Just kind of wrote some things down. Alexander and Hippocrates wrote, they reasoned that the hexagon, being a polygon, can be squared. Each lune from the preceding argument can likewise be squared, and so by the additive process, a square whose area is the sum of half a dozen lunar areas can be constructed, thus the circle on AB can be squared by the simple process of subtracting areas that were earlier noted. Alexander also pointed out a flaw. The lune that Hippocrates squared in our Greek theorem was not constructed along the side of a regular inscribed hexagon, but rather the long side of an inscribed square. Hippocrates provided a process for squaring the kind of lune that arose there. Just a big thing, that the big issue was not whether such square exists, but whether it can be constructed with a compass and a straight edge. And I also, I found a video while we're going through these last few slides. I found a video that I feel like my students, when I show like a quick video, they respond better to the content, whether the video is boring or not boring. It's somebody other than me speaking to them, so I just kind of want to add on to a video that I found on YouTube that talks about the construction and some problems that can be solved with that. So I'm just going to add through the rest of these slides, and then I'm just going to play this parts of this video. All right, we ready? Here we go.
Construct a semicircle with center O. Label one of its endpoints as A, and then construct a perpendicular OB to AO. Now connect A and B together, and let its midpoint be point D. From there, let's construct a semicircle centered at point D. Now consider the area between AEBF and the triangle ABO. What is the ratio between the yellow area AEBF and the blue triangle ABO? This is a famous historical problem. AEBF is called a lune, deriving from the Latin word luna for moon. This is credited to Hippocrates of Chios, who solved this in ancient times, nearly 100 years before Euclid. Now I should mention this is not the same Hippocrates of Kos, who's the doctor of Hippocratic Oath fame. So you might think this is a very basic geometric problem. But remember, this was even before Euclid wrote the Elements. This is said to be the first precise mathematical calculation of an area between curved lines. This is even before the familiar formula for the area of a circle. So, Hippocrates used very basic principles. This was solved using the Pythagorean theorem and the second fact that the area of a circle is proportional to its diameter squared. Using just these principles, can you solve for the ratio between the yellow lune and the blue triangle? I want to thank Sahil Day and Byron from Melbourne who suggested this problem. Can you figure it out? Give this problem a try, and when you're ready, keep watching the video for a historical solution. First, let's label the diameter of the circle as AC. Since ABO is an isosceles right triangle, AB is equal to AO times the square root of 2 by the Pythagorean theorem. We can then deduce that the diameter AC, which is equal to 2 times the radius AO, is equal to AB times the square root of 2. Because a circle's area is proportional to its diameter squared, semicircle ABC has 2 times the area as semicircle AEB. Consequently, half of semicircle ABC, which is the quarter circle AFBOA, has the same area as the semicircle AEB. In other words, the area of this quarter circle is exactly equal to the area of this semicircle. And now we've pretty much solved it. Here comes the magical step. The lune AEBF and the triangle ABO are both found by subtracting the same area, AFBA, from shapes that have equal area, the semicircle AEB and the quarter circle AFBOA. Thus, the lune and the triangle are found by subtracting the same area from shapes of equal area. Therefore, their areas are equal. You can also write this out algebraically, and you will note that these two shapes have the same area, and you're subtracting the same area from each of them. Therefore, the two areas are equal. So I assume you'll be able to figure this out because it's a basic geometrical problem. But it should remind you some of these problems that we find very basic and routine today were challenging thousands of years ago. So I hope this inspires you to solve a problem today which students thousands of years from now will learn in grade school. Thanks for watching this video. Please subscribe to my channel.
Okay, yeah, so to sum up everything, that's my presentation on Hippocrates quadrature of the loon. Like I said, I feel like people really respond to videos, so that's why I chose to use a video. Yeah, thank you.